In this tutorial, we are going to make a brief summary of the three forms to represent a complex number: binomial, polar, and exponential form. And we are going to see how to compute powers and roots of complex numbers. So remember that in order to be able to use the commands complex plot and complex plot bin, we have to make enter to these two lines to read this file. So, brief summary. Remember that we have three different forms: binomial form, which is a plus bi. A is the real part, b the imaginary part, and I is the imaginary unit, such that I squared is minus 1. The polar form is given by r, the modulus, sub the argument, sub theta. The modulus is the distance from the origin, and the argument, theta, is the angle counterclockwise from the OX axis, and the exponential form is a different way of writing the same information as in the polar form, which is modulus times the exponential of the argument times I. So how do we move from one to the other? From polar or exponential to binomial, we have this formula which tells us that if we know the modulus r and the argument theta, then the number is r cosine of theta, r sine of theta I. If we want to move from binomial to polar exponential, so we know the real and imaginary part, and we want to know the modulus and argument. The modulus is going to be computed using this formula, using the Pythagoras theorem, and the argument is going to be computing using the arctangent of the imaginary part divided by the real part. This formula is correct in the first and fourth quadrants. If we are in the second quadrant, we need to add pi, and in the third quadrant, we need to subtract pi. So this is mainly the most important information, but if we don't have a calculator, we need to know the cosine and sine of the most important angles, and also we need to know the arctangents of the principal numbers. So how do we do it? We have to remember this table here, which gives us the angles in the first quadrant, so it's 0, 30, 45, 60, and 90, and then we need to know if we need the sine, cosine of tangent of a number in the second, third, or fourth quadrant. We need to know these expressions. So how to move from the second to the first? We do pi minus the angle, and we change the sign of the cosine. If we are on the third, we just add pi to the argument that we have, but we change both sine and cosine, signums or signs. And if we are on the fourth, we just change the sign of the argument, and then we change the sign of the sine function. Also here you have the table that allows us to compute the arctangents easily. So this is a brief summary. Let's see how we compute powers of complex numbers. Remember that we had this table. So in binomial form, it's very easy to add and subtract. We can do product division and powers, but maybe it's too long, but we cannot do roots. And in polar and exponential, we cannot add. So if we have two numbers in polar form, we need to convert them to binomial and then add. But we can easily compute product divisions, so it will be always easy to compute powers and roots. So let's see how we do it. Let's start with powers. So the first power that we need to compute is the power 2, the square of a number. So imagine that we are given a number which is given in binomial form. In this case, we can compute its square by just using the same formula that we use for real numbers: a squared plus 2abi plus bi squared. So in this case, we get a squared plus 2abi plus b squared I squared. I squared is minus I squared, this one is minus 1, so we get I squared minus b squared plus 2abi. So in binomial form, we can compute powers. What about exponential form? In exponential or polar form, we know the modulus and argument, so we know this expression. And now, what we are going to do to compute the square is we just put r e theta I. So we join the two r's, which are real numbers, and we join the two exponentials. So now, remember that we know how to do products. This we can join the exponentials, so we have the same properties that with real numbers. And what we get in the end is r squared e 2 theta to the power r I. So when we compute the square of a number in polar form, we do the square, we square the modulus, but be careful because the argument is multiplied by 2. Okay, so this is if we want to compute the power 2, the square of a number. So we can do it either in binomial like this or in polar form. So let's do cubic roots. So now imagine that I want to compute z to the power 3. This can be seen as z squared times z. So here, if I want to do it in binomial, what I'm going to take is the expression that I got before, and I have to multiply it again by z. Okay, so this is z squared times z. And now you can see that this can be done, but it's quite large because now I have to multiply a by all this term and then bi by all this term and arrange all the terms. So this is long. So if we can avoid it, in general, we are going to avoid it. But what about in polar form? So now here I'm going to put z squared, and now I again put z. So in this case, now I join r squared r, e to theta I times z theta I, and now I join the exponents, so I have r cubed e to theta I plus theta I, which is going to be r cubed e 3 theta I. So as you can see in this case, if we want to compute the cubic, if we want to raise a number to the power 3, it's very long to do it in binomial in general, but in polar it's very easy. So we take the power 3 of the modulus, and the argument is multiplied by 3. So now, having a look at this, so what we have obtained is that, we have it here, if z is r e theta I, z squared is r squared e 2 theta I, z cubed is r cubed e 3 theta I. So we can deduce a general formula. So we have that z4 to the power 4 is going to be the modulus to the power 4 and the argument multiplied by 4. Z to the power 5 is going to be the modulus to the power 5 and the argument multiplied by 5. And in general, z to the power n is going to be the modulus to the power n and the argument multiplied by n. And this is the Moivre's formula. So we have a number in exponential or polar form in exponential. If we want to raise it to the power n, we raise the modulus to the power n and we multiply the argument by n. So it's modulus to the power n and argument multiplied by n. So let's prove this formula by induction. So we want to prove that if we are given a number z, which is r e theta I, then we have the formula that zn, the power n of z, is rn e n theta I. Okay, so to do it by induction, we do the base case, which is n equal to 1. So we take the formula, substituting n by 1, so we get e theta 1, which is theta. So it's true that z to the power 1 is z. So in this case, the base case is true. Okay. So let's do the induction case. So assuming that the formula is true for n, let's see that it's also true for n plus 1. So let's assume that Zn is equal to Rn e to the power n theta I. So this, we assume that it's true. We want to see if, when we substitute by n plus 1 in the formula, this is also true. Okay, so we assume that this is true, and we want to see if this equality here holds. Okay, so now z to the power n plus 1 can be written as zn times z. And now, if we use the induction hypothesis, so I'm going to say that this is the induction hypothesis, so Zn can be substituted by Rn En theta I. And now I'll multiply again by R. Okay? So now we have used the formula that we know that it's true, that we assume that it's true, and now we just have to join what we have. We have R to the power n times R, En theta I times E theta I. So this is R to the power n plus 1, E to the power n theta I plus theta I. So again, if we join them, we get R to the power n plus 1, and now this is E to the power n plus 1 theta I. So this is what we wanted to see. So this equality here is true, and the proof is concluded. Okay? So we have proved by induction that De Moivre's formula is true. Okay? Now, what do we have if we recall the operations? When we multiply two complex numbers, we multiply the modulus and we add the arguments. When we divide the modulus and we subtract the arguments. If we do the conjugate, we just change the sign of the argument. And when we do powers, we raise to the power n the modulus, but we multiply by n the argument. So now that we know how to do powers, let's do this exercise. So in this case, we take z1 to be 1 minus I, and we want to compute z1 square. In this case, since it's just a square, we can do it in binomial form. So this is going to be the square of the first minus 2i, 2 times the first times the second, plus minus I square. This is going to be 1 square minus 2i plus I square. I square is minus 1, so I get this one minus 1, so it's minus 2i. So in this case, if we are given the number in binomial form, it's easier to do the power 2 also in binomial form, but we can also do it in polar because this number is quite easy. So this number is 1 minus 1. So this number here is z1, 1 minus I, which is equivalent to the point 1 minus 1. So the modulus in this case is going to be square root of 2 because it's the hypotenuse of a rectangle triangle, and the argument we can compute it just by looking at it. It's minus 45 degrees because A and B are equal. So it's minus pi over 4. So in this case, z1 is going to be square root of 2 e to the power minus p over 4i. So once that we know this, z1 square is going to be square root of 2 e minus pi 4 square. So this is, we raise the modulus to the power 2 and we multiply by 2 the argument. Okay? So this is going to be e to the power minus pi over 2i. So now let's see if this is the same. What about this number? This number is a number which has modulus 1 and argument minus pi over 2, which is minus 90 degrees. So if I have this and I do minus 90 degrees, I get this number here. So this number here is e minus pi over 2i, which is minus I. So if I substitute this in here, we get 2 minus I, which is minus 2i, which is the same result that we got on top. If we want to check it with Maple, we just have to do this, z1, and then we take its power 2. Okay? So now what we get is we directly do its power, and Maple computes it. And we can also, if we want, we can convert z1 to polar, so that we get modulus square root of 2 argument minus pi over 4. And then if I do square root of 2 exponential of minus pi over 4i, pi in exponential form to the power 2, there's a missing parenthesis, I get this expression, which I can simplify, Control L to put a label, which is going to be 3.4, and I get the same number, minus 2i. Okay, this is the first exercise. Second exercise, we need to compute the same number but to the power 10. Okay, now in this case it would be best if we do it in polar, but in this case we can do a trick, because the square of the initial number is quite easy, so we can rewrite the power 10 as the power 2 and then the power 5. So in this case would be minus 2i to the power 5. Now I can do minus 2 to the power 5, I to the power 5, which is minus 2 to the power 5. And now I rewrite I to the power 5 as I squared, I, so it's minus 2 to the power 5 minus 1i. So it's going to be minus 2 to the power 5i. So even though in this case it would not be in principle as easy to do it in binomial form, since the square is easy, we can do it. Okay. Now if we do it in polar, which is the one which is really easy to do, in polar form, okay, this was, or the exponential, we got this number, square root of 2e minus pi over 4i to the power 10. And remember that this is just the modulus, we raise it to the power 10, and the argument, we multiply it by 10. So in this case we get 2 to the power 5 e minus 5 pi over 2i. Okay? So now this number, this argument, is not a principal argument because it's smaller than minus pi. So what I'm going to do is I'm going to add 2 pi I. I'm going to add one circle rotation, so I get 2 to the power 5 e minus 5 pi plus 4 pi over 2i, and this is going to be 2 to the power 5 e, sorry, this minus is on top, e minus pi over 2i. Okay, again, e to the power minus 2, we got it from before, it's minus I, so what I get is the same result than before when we do this, minus 2 to the power 5i. Okay, so now we can check it, see if I do z1 to the power 10, what I get is minus 2, 32, which is 2 to the power 5i. Okay, minus 32i. So let's do the last exercise, which is this one. We are going to define z2. In this case we have a number in exponential form and we have to compute its power 6. This is going to be easy. So as we do it, we raise the modulus to the power 6 and we multiply the argument. So in this case, if we do the result is 4096 e30i. So now 30 is not one of the principal angles or the most important angles, so we have to leave it as it is. We cannot simplify it. Okay, so if we do it with Maple, so if we do 4 exponential of 5 times I to the power 6 here, what we get is this one. We can evalc it to convert it to binomial, and as you will see, since 30, the power 30, this one, is not one of the principal arguments, if I convert it, I would get to binomial, I would get the modulus times cosine of 30 plus sine of 30i, and this, so in radians, remember that 30 radians, okay? We always use radians, so this is can just be computed using a calculator, otherwise we leave it as it is. So now you can move to do the exercises from the test. So let's do roots. So now we know how to do powers. Let's compute roots. So again, this is very important. Even though we can compute powers in binomial, maybe it's too long, but we can do it. We cannot compute roots in binomial. So whenever we have to compute roots, we need to move to polar or exponential. Okay, so let's see this definition. if z is an nth root of a complex number a, if this equation holds, if z to the power n is a. When we work with complex numbers, we will avoid the notation that we use with real numbers, which is that z is the nth root of a. We are going to avoid this notation because this in general represents only one number, and we want to see that this equation, when we are working with complex numbers, has more than one solution. Okay, so let's see what we got with real numbers and what we are going to get with complex numbers. So imagine that I want to solve these equations, x to the power n equal to a, when now instead of a z I put an x because I assume that is a real number. Okay, so if I have an even power like 2 or 4 and a is positive and the one in the right hand side is positive, I have two solutions in the real number. So for instance, x squared equal to 1, the solutions are plus minus 1. X to the power 4 equal to 16, the solutions are plus minus 2. If n is even and a is equal to 0, I just get one solution, which is 0. If n is even but a is negative, we don't have a solution. So x squared equal to minus 1 or x to the power 4 equal to minus 16 do not have a solution if we are working with real numbers. And if n is odd, we always have one solution. So these equations, for instance, x cubed equal to 1 has 1 as a solution. x5 equal to minus 32 has x equal to minus 2 as a solution, or this one has 0 as a solution. So if we work with real numbers, these kind of equations can have different number of solutions: 2, 1, none, or 1. What happens if we work with complex numbers? When we work with complex numbers, the equation z to the power n equal to a will always have n solutions. Okay, so for n equal to 2, we have two solutions. This means that all numbers have two square roots. So in this case, x squared equal to 1 means x equal to plus minus 1. And now x squared equals to minus 1 has a solution plus minus I. Okay? For n equal to 3, we have three solutions, always. So all numbers have three cube roots. In this case, x cubed equal to 8, for instance, has these three solutions. The real one, 2, and then these two complex solutions. So we have three solutions. If n is equal to 4, we have four solutions. So all numbers have four fourth order roots. So x to the power 4 equal to 1 has a solution plus minus 1, but also it has plus minus I. So in general, this equation, when we work with complex numbers, has n solution, and this means that every complex number a has nth order roots. Okay? So how do we find this solution? So the important thing is, how are we going to find this? So here you have this proposition. If we have this equation here, so z to the power n equal to, this is going to be a. This represents the a as in the previous equation. Remember that any complex number we can has an infinitely many number of arguments, so we can add as many circle rotations as we want. So this is the same. So this equation has, as we have said, n solutions. And which are these solutions? With the modulus, we take its nth order root. And with the argument, which is this one, we divide it by n. And this holds for these values of k, which is 0, 1, 2, 3, up to n minus 1. Okay? So we have that these are the n solutions that we are looking for. And an important thing is that the solutions are placed in the vertices of a regular polygon. So all the solutions have the same modulus, which is this one. And the argument is separated by an angle of 2 pi over n, this one here. So let's prove this proposition. So let's prove that the solutions of the equation z to the power n equal to r e theta I, r z equal to, we take the nth root of r, remember that this can also be written as this one, and then when we multiply, when we take powers we multiply by n, when we take roots we divide by n. So we just divide this by n, and then the k goes from 0, 1 to n minus 1. Okay, so in order to see this, we need to see that indeed z to the power n is this one. Okay, so let's take the z that were given and make its power. So we take this z here, and we raise it to the power n. Remember that when we make powers, we take the power of the modulus and that we multiply by n the argument. So now we simplify the two roots. This is r. This is because r is positive. And then when we multiply, you can see that this n goes back to this one. So we have theta 2 pi k over I. And now these are circle rotations, so that this can be removed. This is the same as this one, as we wanted to prove. So as we have seen, this expression here provides the solution of the equation we wanted to solve. Let's compute the cube roots of this complex number. Okay, so we have z, which is going to be 4 square root of 3 plus 4i, and we want to compute its cube roots. Okay, so as we know, we have three solutions, okay, because we are dealing with cube roots. So in this case, we look for z1, z2, and z3 such that when I raise any of these numbers to the power 3, we get the original number. So the first thing, remember that we can only do it in polar form. So the first thing that we need to do is convert to polar. So we have this number here. Remember that it's always important to make a plot. So we have 4 square root of 3, 4. So we have a number in the first quadrant, okay? This is very important because we know that the argument is going to be between 0 and pi over 2, okay? So now let's compute the modulus, which is the square root of 4 square root of 3 to the power 2 plus 4 square, which is square root of 16 times 3 plus 16. Okay, this is equal to square root of 16 times 4, which is 4 times 2, which is 8. Okay, we can check it here. So we define the number, and with the ups command, we can see that indeed the modulus is 8. Okay, now the argument is going to be the arctangent of the imaginary part 4 divided by 4 square root of 3. Okay, in this case this is wholes because we are in the first quadrant, so we don't have to add or subtract by. So what we get is the arctangent of 1 over square root of 3. So now remember that we always have to have this table written in the exam. If we go to the tangent and we look for 1 over square root of 3, we get an angle of pi over 6, which is 30 degrees. So this one here is going to be pi over 6. Okay, so now we know that our number z is 8 e to the power p divided by 6i. So the roots, let's use the formula. So the first root is going to be the cubic root of 8, the cube root of 8, and we have to take the modulus, the argument, sorry, and divide it by 3. Okay, remember that when we have this formula, we do the cube root and we divide by n. Remember that in this case, n is equal to 3 because we are doing cube roots. Okay, so what we get is 2e to the power pi divided by 18i. Okay, so now if we again make a plot, so we are going to get something like this one. This is going to be z1, and the important thing is that we know that the other roots are placed in the vertices of a triangle, of a regular triangle. So we have here a circle, in this case of radius 2. This is going to be z2 and this is going to be z3. So if this is a regular polygon, this means that this angle, and this angle are going to be the same. So I always like to see them as a pi, un pastis. So if we have a total of 2 pi angles and we want to do 3 equal pieces, these angles are going to be 2 pi over 3, 2 pi over 3, and 2 pi over 3. Okay, so when I want to move to the second root, I'm going to have the same modulus, and the argument is going to be the original one, this one here, plus 2 pi over 3. This is equivalent to take the formula in the formula k equal to 1. So in this case, what we are going to get is 2. And now let's do it in here. So I'm going to do pi over 18 plus 2 pi over 3. Okay, so it's going to be 13 pi over 18i. So this is going to be the second one. So if I have the first root, okay, this is going to be the first root here. Modulus 2, an argument pi over 18. The second one has the same modulus, and we add 2 pi over 3. Okay, the third one, so in order to move to the third one, we can either go from the second one to the third or from the first to the third. I always move forward, so what I'm going to do is take z2, which is this one, and again add 2 pi over 3. Okay, so again I add 2 pi over 3, and what I get is e to the power 25 pi over 18i. So this is not the principal argument, so I can subtract 2 pi over I to get the principal argument if I need it. So I subtract 2 pi, and what I get in the end is 2 to the power e minus 11 over 18 pi over I. So my three roots are z1, modulus 2, argument pi over 4, z2, same modulus, argument 13 pi over 18i, and the third one is 2 e minus 18 over pi I. Okay, so let's do the third one. So here when I did z2, okay, this was z2, and then z3 is gonna be this one. Okay, so these are the three numbers that we got. So now we can make a plot, and if we make a plot, you will see that indeed this is z1, z2, and z3, and the three complex numbers are placed in the vertex of a regular triangle. Okay, we can check it, so we can now do the power 3. We can compute z1 to the power 3, z2 to the power 3, and z3 to the power 3, and we can see that we get the original number in both three cases. Okay, so let's do next exercise. So in this case, we are given a number z, which is going to be 1 minus square root of 3i, and we are supposed to compute its 5 fifth order roots. So in this case, n is going to be 5. So again, the first step is to convert to polar. Okay, so we have this number here. Very important to make always plots. 1 square root of 3. So I can make it a little bit better because this is not the same distance. So I have this number z, okay? Now I know that I'm on the fourth quadrant. So the modulus is going to be the square root of 1 plus minus square root of 3 to the power 2, 1 plus 3 square root of 4, which is 2, and the argument is going to be the arctangent of b divided by a. Remember that the arctangent, you can take out the minus sign, and now we move to the table. So square root of 3 is pi over 3 minus pi over 3. So this is minus 60 degrees. Okay? This is our number. So we know that z is 2 e to the power minus pi over 3 I. Okay? So now we know that since we are computing fifth order roots, we have 5 solutions. The first one is going to be the fifth order root of 2, and now we take the argument and we divide it by 5. So this is square root of fifth order root of 2 e to the power, this is a product, minus pi over 15 I. Okay, so let's make a plot. Maybe it will not be a very good plot. So this is going to be my first angle. Okay, this is going to be like in here. So now I know that I have 5 other roots which are placed in the same circle, but because we have the same, this is a circle of modulus square root fifth root of 2, and we have to put them divided equally. So now I'm going to do something like this. It's not going to be a good plot. 1, 2, 3, 4, and 5. So in the end, if we make a good plot, this is going to be a pentagon, okay? A regular pentagon. So if I have a total of angle of 2 pi, this here, this here, this here, this here, and this here is going to be 2 pi over 5, okay? So if we do it, z2 is going to have the same modulus, and I take the original argument and I add 2 pi over 5. Okay, so if I do it, what I'm gonna get, let's do it in here. So let's check that we did it correctly. Square root of 3 times I. So we convert z to polar. And now once we have this, okay, let's do z1. z1 is gonna be the fifth order root of 2, and we divide the argument by 5, okay, because this is the n. This is minus pi over 15. Now z2, I have the same modulus, okay, and now I'm going to add 2 pi over 5, and this is going to be, if you do it, pi over 3i. So this is going to be z2. Now z3, I move from z2, I take the previous one, so I'm going to take pi over 3, and I'm going to add again another angle. So what I'm going to get is, I'm going to do the same. Okay, z3 is going to be the same, but I add again this one, so it's going to be fifth root of 2 e to the power 11b. This is still an angle which is given in its principal form. Let's do z4 is going to be the fifth root of the previous argument plus again 2 pi over 5. So what I get now is z4, I do the same, I add again 2 pi over 5, and I get this one, e to the power 17 over 15 pi I. Don't forget the I, never forget the I. So now if I want to get the principal argument, I need to subtract 2 pi. So this is going to be equivalent to the fifth order root e minus 13 over 15 pi I. Okay, and now the final one, the fifth one, okay, z5 is going to be square root of 5 of fifth square root of 2. And now I take the previous argument and I add 2 pi over 5. Okay, so I again add 2 pi over 5. And I get that this is going to be e to the power minus 7 pi over 15i. Okay, so one important thing is that now what I can do is I can check if z1 to the power of 5 is what if I simplify it. Okay, what I get is the original number that I got, so the z1 is correct. If I do z2, also correct, z3 also correct, z4 also correct, z5 also correct. Okay, if we want to make a plot, I just need to copy this, and I'm going to add 3, 4, 5. Okay, and then I need to add also 3, 4, and 5. And I'm going to get the well-plotted pentagon that we were talking about. Okay, and finally the last exercise is to compute the fourth order roots of z equals 16. In this case, the number that we are given is very easy because 16 is in the real axis on the positive part, so the argument is going to be 0. So this is going to be modulus 16, sorry, theta no, 0 times I. Okay, so z1 is going to have the fourth order root because n is equal to 4 of 16, and the first argument divided by 4. So we have 2e0i, which is 2. Okay, z2, now we can finish the exercise because in this case if we have, sorry, if this is 16, this is going to be 2. So we know that the roots are placed on the vertices of a rectangle. So in this case it's going to be 2i minus 2 minus 2i. So we can finish the exercises like this by just knowing that the roots are on the vertices of a square, but we can also do it in the same way. So again, in this case we have 4 roots, so the distance between the arguments is going to be 2 pi over 4. So we have it like it is. So it's e pi over 2i. This is 90 degrees modulus 1. So this is I. So this is 2i. Z3 is going to be the previous one plus 2 pi over 4. So it's going to be 2 e pi I. Pi is modulus 1, argument minus 180 or 180. So this is minus 1. So this is 2 times minus 1, which is minus 2. And z4 is going to be 2 e to the power pi over 2, pi, the previous one, plus 2 pi over 4 I, which is going to be e to the power 3 pi over 2. We can subtract 2 pi, so we get minus pi over 2i. So this is minus I, so this is minus 2i. So the solutions are 2i, minus 2, and minus 2i. If we can do the exercise by just making a plot, we can justify it and we don't need to do anything else. So let's do the exercises and let's make the plot. Okay. So what I'm going to do is I take z equal to 16. I convert it to polar, so you can see that we get the result that we got, modulus 16, argument 0. Now we take the first root, so I take this polar form, and the first root is going to be the fourth root of the modulus and the argument divided by 4. This is the first root. The second root is the first one plus 2 pi over 4, which is going to be this one. Next one is going to be the previous one, and I add again 2 pi over 4, so it's pi. And the fourth one is going to be, I add again this one, which is 3 pi over 2. Okay, so this is not the principal argument. Remember that I can subtract pi, minus 2 pi, so this is minus pi over 2. And now if I make up the plot, I just need to remove the fifth point from the previous example. And as you can see, we get 2i, minus 2, and minus 2i. So now you can proceed to do the final exercises, and if you have more time, you can do these exercises given here, 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 and here.